excited to help coordinate these workshops. These workshops are eligible for AIA credit, and therefore we are showing you the typical AIA language. So there are no expressed or implied endorsements of any products as part of this. Because this is an AIA presentation, this copyright notice is provided. Well, I am excited about today's topic. We're really talking about no more boilers is the topic, but we're talking about how to eliminate or at least reduce combustion in healthcare. The format for today is really interesting. We have a couple of quick presentations. Jim Crabb, supported by Walt Vernon, and then Mark Stavig, Dr. Monica Weiss, and Dr. Riyad Swapta will be presenting on some interesting topics. At that point, we'll very quickly put them into discussion. This is rapid fire, and then you'll have the opportunity to go into a breakout room. So what we'd like you to do is to post in the chat the room that you are most interested in attending. We'll try to get you into that room, and in that room, you'll have an opportunity to first think big and think of all the different ways we can eliminate combustion. We'll brainstorm similar to last time, and then we'll focus in on the particular topic of that room and understand the challenges, opportunities, and how to overcome those challenges so that we can move some of these things forward in healthcare. So that's the agenda. We'll come back together, share. You'll be reminded of the great resource we have in our online community, and then we'll tease the next workshop. I'm excited to introduce this overall concept. It is simply that we have the opportunity, once we eliminate reheat, to find other ways to reduce combustion in healthcare. And with that, I'm going to turn it over to our first speaker, Jim Crabb. Take it away, Jim.
Thank you, Troy. So when we talk about decarbonization, one of the things we talk about is eliminating on-site combustion of fossil fuels, or put simply, electrify everything. And that has caused some concerns about electrical capacity of the grid itself and the electrical systems of our hospitals. And certainly if we just convert all gas-fired equipment to electricity, we would have a problem. But that isn't really what we mean. So what we're going to talk about today is the why and how we can electrify these loads without overloading the electrical system. So what you see here is a different view of the pie chart that we looked at in our last workshop that shows the energy uses in a typical hospital by end use. And in that last workshop, we talked a lot about reheat as the dominant energy use in a typical hospital. I have reformatted this to be about carbon emissions. And what you see here is above the net zero line is the carbon emissions of the combustion systems, and below the line is carbon emissions from electricity. This is done to scale, but it's scaled for California. If this was in a different part of the country, the bottom part of the graph for electricity would potentially be quite a bit larger because the electrical grids in other parts of the country can be quite a bit dirtier. California isn't the cleanest, but it's pretty darn close. But once again, even in terms of emissions, reheat is the dominant load. Click. I have an automatic clicker here. In that last session, we talked about ways to reduce reheat. And what I've done here is I've just arbitrarily said we'll cut reheat by 50%. That's a pretty reasonable assumption. We can actually do better than 50%, but let's just start there. We're going to have some reheat probably as long as we have minimum airflows in hospitals. And we're also going to have heat needs, and heat and reheat kind of got dumped together here. So that's fine. That's a nice substantial reduction in carbon emissions. Click. But The problem with doing that with natural gas is that it never gets any better. We're locking in carbon emissions for decades. And as we know, many parts of the country, including California, have made commitments to reduce the carbon emissions of the electrical grid to 50% by 2030 and net zero by 2050. So the carbon output of the electrical systems in buildings will head toward zero, but combustion systems never get any better. The emission rates on day one will continue for the life of that equipment, which could be 20, 30, 40, even longer. So we could think about transitioning from old steam boilers to high efficiency condensing boilers. And that would be an improvement, but the improvement is only maybe 10% better. So that doesn't really change this picture in any significant way. So we could say, well, let's convert all of that heating to electricity. If we did that in California, that would be effectively a carbon neutral transaction, but it would also be very expensive to operate and would put a pretty large load on our electrical systems. But there's a better way. This is where heat pumps and heat recovery chillers can come in. We use chillers all the time to remove heat from the building. Mechanical engineers here know that a chiller is really the same thing as a heat pump. It moves heat from a low temperature to a higher temperature where we can do something with it. Those of you that heat your home with a heat pump know that you're sucking heat from the cold outdoors and raising the temperature to keep your house warm. In the case of a chiller, we raise the temperature so we can throw heat away with a cooling tower. With a heat recovery chiller or a heat pump chiller, we're just raising the temperature a little bit farther so that we can make hot water to heat our building, whether that's for reheat or actual heating. We're using the heat pump in this case to do something useful instead of just throwing all that energy away. Click. So heat pump chiller uses about a third of the energy of a boiler. So we've made a pretty significant reduction there. And that's really what we mean by electrification. When a chiller operates in the heat pump mode, it does use more energy than a cooling only chiller, but still only some of the chillers need to operate as heat pumps. And so the impact on the peak electrical loads for a building is really quite small. Click. And so what happens as we convert to electrical energy is that we get to take advantage of the improvement in the electrical grid on the heating side as well. But you'll notice there's still one end use here that the heat pump really can't help with, and that is steam for sterilization and humidification. But stay tuned, we're going to talk about that in an upcoming workshop. So this works out pretty well on an annualized basis. We have more than enough energy available. But where do the heat pumps get the heat that they need to move into our building where we can use it? Well, first, let's look at all the energy we're putting in the form of electricity. Lighting, equipment, plug loads, HVAC fans. We don't think of that as heat because we use different units when we talk about electricity. But kilowatt hours and BTUs are really just different names for the same thing. So most of the energy we put into the building ends up as heat that we currently have to throw away, either through chillers or through economizers. But we could harvest that heat and put it to use. In winter, we sometimes run airside economizers instead of chillers. That's great, it's free cooling, but what are we actually doing with that economizer? We're just throwing heat out through a louver and bringing in cool outdoor air to absorb the excess heat we have in our building. So instead of throwing heat out the louver with an economizer, we could operate a heat pump chiller to harvest it for the heat that we need in our buildings. And we've actually done this. We've built 2 hospitals in Georgia that you don't use any fossil fuels for heating the building. What we've found is that those buildings have excess heat almost year round. It does sometimes get below about 25 degrees here, and when we get to those temperatures, we go into net heating mode. But in California and in most of Georgia and many other parts of the country, we don't really get below 25 very often. But there are times, climates where that does happen. And when that happens, we need additional heating sources. So we have several panelists here today that will talk about technologies that we might use for either primary or supplemental heat, or to store heat when we have excess so that we can use it when we need it. But first, we need to talk about the capacity of our electrical systems. And for that, I'm going to turn this over to Walt.
Thank you, Jim. You will notice, by the way, that I'm wearing my down jacket because we don't heat our house. I'm trying to decarbonize. For those of you on this call who don't know me, I am an electrical engineer. And I get a cameo appearance to talk about electricity on this panel. And I just wanted to reflect on a couple of things. Particularly here in California, we have a large proportion of our hospital buildings are now new buildings, largely because of Senate Bill 1953 and what that's done in terms of replacing buildings. And one of the things that I think many of us are aware of is that the building electrical systems in most of our buildings, when they first open, we will run at roughly 20 to 30% of our actual capacity. Generally speaking, for whatever reason, our systems tend to be designed with ample capacity in them. And so I'll start by just recognizing that, sort of that simple fact. There's obviously complexities, even in electrical engineering. As we move into the future and we are thinking about things like electrified transportation and electrification of these kinds of systems, there are changes that are going to occur. There are the issues about normal power versus emergency power and where is the capacity, or the capacity at the service versus the capacity at a local distribution panel. And what I would mostly like to say is it's okay, don't worry about it, we'll figure it out. That generally speaking, I think capacity is not going to be an issue. I think actually maybe system configuration and design may be an issue. I do a lot of work on the National Electrical Code with NFPA 99 is we're starting to think about what is the electrical distribution system of the future need to look like. And I think for the purposes of a decarbonizing conversation, the last thing you need to worry about is, will we be able to figure out how to find electrical capacity for it? And one of the things that we know for sure is that in California in particular, the CEC is pushing us towards electrification, and the governor is pushing us towards electrification and to continued progress at reducing combustion and carbon into the atmosphere. And so in some ways I would say it doesn't even matter if there's capacity or not capacity. We are engineers, right? That's our job, is to figure out how to make it work. And I think this should not be an issue. So maybe the last thing I'll say about all this, it is an interesting policy question, not for us so much at a building level, but at a policy level about the grid and the grid capacity if we all of a sudden quit using natural gas and start using electricity. I'm sitting here in Marin County, and we're talking about a new buildings all electric code for our new buildings, right? And so these kinds of questions are on everybody's minds. But I think as we continue to develop new solutions for on-site generation, I don't think we need to worry about the electrification issue. We need to just go and do it. And so with that, I want to hand the baton back to those of you who can figure out how to get it done.
Okay. Awesome. Thank you, Jim and Walt. We're continuing with our rapid fire. We'll next hear from Mark Stavig, a mechanical engineer, who's going to talk about geothermal heat pumps. Take it away, Mark.
Thanks, Troy. You can slide to the next. What I'll do is I'll talk about a case study on how we applied geothermal heat pumps on a project that's been open about 7 or 8 years now. It's a small 40,000 square foot hospital up in the San Juan Islands, a beautiful part of the country, kind of northwest Washington state, kind of assignment between there and Vancouver Island. You can see the facility on the right, several wings. The actual well system is in the parking lot on the bottom right-hand corner of that photo. So you can go to the next slide. This project, it was a great opportunity for this project for a couple of reasons, one of which there was no natural gas on the island, so that led us away from the carbon challenge we would have. But we also, the design team, the architect, the contractor, the owner were very committed to energy savings, and so we followed this living building challenge, which had a net zero energy goal for the project. And so we decided that the best opportunity to go with would be with a ground source heat pump system. The original thought was we can trying to get to EUI of 55 and energy use of 55. Due to budgeting and some other issues, it ends up operating somewhere right around between 85 to 100. Kind of depends a little bit upon how active the hospital is at the time. The systems, they're kind of broken up into decoupling and minimizing reheat, all those things to help minimize the impact on a system to allow our heat pump system to operate as efficient as possible. And so the photo on the right is the mechanical room during construction. You can see it's pretty condensed, lots of piping, lots of small distributed systems that allow for a system to be tailored to the use of the space. So Troy, next. I'll get a little geeky here. This is the piping diagram, but I think it explains how the heat pump system works. Again, just like what Jim was talking about, the heat pump, transfers heat from one source to another. So the 4 blocks in the middle, those are the actual water to water heat pumps. The 2 on the left are in cooling mode pretty much most of the year. The one on the right in brown is in heating mode most of the year. And then the third one, or the second one over from the left, is kind of splits between heating and cooling mode depending on the time of year. And so what they're doing is each of these heat pumps are creating either a chilled water or a heating water that's being supplied out to air handlers and fan coil units distributed throughout the hospital. And so they're rejecting their heat to that blue box at the top, whether if they're in cooling mode, they're rejecting heat into that loop. If they're in heating mode, they're rejecting essentially cooling into that loop. And so that loop in the middle is the condenser water loop that kind of circulates and during certain times of the year, the spring and the fall, it kind of is self-supporting. They get heats from the ones that are providing cooling and cooling the ones providing heating. And so it kind of self-works its way around. During the times when that loop doesn't maintain consistency, the green loop on the left is where the ground source comes in. So the ground source, what it's doing is it's circulating water out to a well system. There's 22 wells. They're 300 feet deep, bored into the ground, like I showed in the parking lot area. And they provide about 2.5 tons of cooling. Essentially what happens is they're pulling water off of that center blue loop, going out there, distributing it into the ground, and it comes back about 10 degrees, either cooler or warmer, depending upon the source and need. It's kind of like what Jim was talking about, the air system, if it's cold enough, you can't get quite as much cooling or heating out of the heat pump. Well, the water and the ground is always about 50 degrees. So it's a source we can use all the time. And so as the green loop conditions that center loop to keep the heat pumps operable and keep that condenser water loop within range, it satisfies the load. It's been working really well. We get printouts, and so the EUI is consistent with what we were thinking. We do have on the right that orange area is the essentially the backup electric boilers, which is code required FGI, and so I don't think they've ever had to come on. So that's kind of how the system works at the facility. Next slide, Troy. And kind of what Jim talked about earlier is condensing boilers at 99% efficient, they're 99% efficient, where a heat pump, if it's running at about 2.4, you can see that it's 2.5 times more efficient than a condensing boiler. So not only are we, not burning fossil fuels, but it's a very efficient operation. So that's a case study of Peace Island.
Great. Thank you, Mark. I am now incredibly excited to introduce Dr. Monica Weiss, who is going to talk about solar thermal systems. She'll share a little bit. Her knowledge on this topic is deep. Go ahead, Dr. Monica.
Hi, everybody. I'm pleased to provide you general information on solar thermal technology and its potential for decarbonizing healthcare and also large buildings. I am co-founder of Erxol, and our company is specialized in integrating solar thermal heating and cooling systems for commercial and industrial applications. Whether for process heat, cooling, refrigeration, desalination, wastewater treatment, domestic hot water, or space heating, provide the necessary technology and the services required for complete solar thermal solutions. The energy assessment, engineering and design, system components to installation, monitoring and maintenance. So the term solar thermal is used, and maybe you can move to the next slide, please. It's a very principal diagram here. So the term solar thermal is used to refer to a variety of different technologies, capturing the sun's natural energy to produce heat energy. Collectors, which gather the sun's radiation, are a key element in all solar thermal applications. The mounted solar thermal collectors harness the free and readily available solar energy to heat a transfer fluid. The solar radiation is transformed into heat energy within the fluid, providing carbon-free heat energy to the specific application. A broad variety of concentrating and non-concentrating solar thermal collectors are available. In principle, the solar thermal collectors differ in supply temperature, application potentials, efficiency, transfer fluid, operating pressure, wind load, energy density per square foot of installation area, maintenance, and building integration options. The sun's energy arrives at Earth primarily in the form of heat. Solar thermal technology collects, stores, and distributes heat energy most efficiently. This heat can be used to heat air or water or other transfer fluids. This process significantly offsets the use of fossil fuels, including natural gas or utility-generated power. At the same time, there are immediate reductions in greenhouse gas emissions from eliminating these energy sources. Solar thermal energy is an elegant solution that can be customized and optimized for many applications, providing a carbon-free heat source for heating and cooling systems. Highly efficient solar thermal collectors harvest the sun's energy with higher efficiencies than PV, 3 to 4 times more, are reliable and flexible in its applications. Carbon-free heat energy can be integrated into central utility plants, into a supply return loop, or directly applied to specific operations such as sterilization, dialysis, laundry, kitchen, and so on. The heat energy can be used for space heating or for thermally driven chillers, eliminating ozone-depleting refrigerants. In combination with the thermal energy storage, it could be either on the cold side or on the hot side. The solar thermal heating and cooling systems optimizes the load profile to meet operation needs and to balance between high and low energy demands. So localized energy efficient heating and or cooling systems can be designed for new and existing buildings and operations. I also included information on the energy density. So the roof real estate is often in short supply. Choosing the collectors for larger projects is critical. So collectors in larger projects are frequently mounted on angled supports on flat roofs to be aligned at an optimal angle with the sun. When installing several rows of collectors, sufficient clearance needs to be considered to prevent shading. I also would like to touch on some metrics that might be important for the energy designers. Depending on the location, the solar radiation, the system integration potential, temperature levels, the delta T, storage, etc., the annual solar yield could be anywhere between 300 to 500 kilo-BTU per square foot. Please get back to me for any questions, and we certainly are interested to learn more about your initiatives and activities and how our company can support and maybe partake in your efforts. So thank you so very much for providing the opportunity to present.
Thank you, Dr. Weiss. I now have the honor of introducing Dr. Riyad Swafda from Phase Change to show us another technology. Take it away, Dr. Swafda. Oh, Dr. Swafda, if you're speaking, you're on mute. Oh, Dr. Swafda, there you go.
They're not ready. They're not ready yet.
I have to go. I have to go.
Okay.
They started.
Okay.
Thanks. Bye.
Oh, Dr. Swafda, go ahead.
Yes. Hi. How are you? So I know we have 3 minutes. So I just sent you 2 slides. So I will just scan through the basics, and I will focus on the thermal energy storage.
Great. Perfect. Yeah, your slides are on the screen. We're excited to hear from you.
Oh, you want me to start?
Yes.
Oh, good afternoon. So my name is Riyad Swafda. I'm the Chief Technology Officer for Phase Change Energy Solutions. I'm delighted to be presenting to the group today. So my first slide is focusing on some basics on phase change materials. In general, phase change materials are substances that can store large amount of energy that can be released or stored at a specific temperature. Ice and water is a perfect example. Today, we have the ability to make ice-like material that can go from -50 to 175 degrees C. And recently we expanded that range to -75. Our technology is based on plant-based, biodegradable, many applications today on the market, from building to pharma food. We provide delivery for Chick-fil-A, for McKesson, Cardinal Healthcare. We have smart refrigeration shelves for the freezers and refrigerators to keep them at the right temperature when power is interrupted. Next slide, please. The second application, which I think is relevant to this group, is thermal energy storage. So today, the company, we provide thermal energy storage in bulk for commercial and industrial applications. We have modular system that 5, 10, 25, up to 50 ton-hour that can be rolled on wheels through commercial elevators. We can also have 500, 600 ton-hours. The key advantages of our technology that you can store the temperature or the energy at the right temperature for whatever application you want, cold or hot, from -50 degrees, or even for thermal energy storage at waste heat recovery applications. I show you here 3 applications on the right corner. We are showing that in an application in California, in a 104-degree day, we were able to store energy in the tank and use it in the mid-afternoon. This is before the peak demand shifting was shifted to the night. And the last example on the bottom is showing you that you could add that into solar thermal, store the energy during the day and use the sun at midnight. And a third application, which is at the center, is the heat recovery, where we can store temperature at 80, 85 degrees C and recover it with very little loss into being used for heating and dehumidification for plant, for cafeterias and so on. I know we are only have 3 minutes, so I'll stop here and thank you for the opportunity.
Perfect. Thank you so much to all of our rapid fire speakers. I think they've told an interesting story, right? So Jim started off by saying the story is that even when we eliminate some reheat, there's more opportunity we need to take advantage of. We can take advantage of that using innovative technologies, right? So things like heat recovery chillers, like using the power of the ground in geothermal. Of using the sun in new ways with solar thermal, of using the material properties of substances to set a particular change energy, like phase change is doing. These are examples of the type of solutions that might help in healthcare. Just before we break out into breakout rooms, I wanted to give one quick question to our to Jim to start off, and maybe one other panelist to respond. Jim, based on what you've heard today and the model that you set up, are there ways you can see in which these technologies might integrate to help us eliminate combustion in hospitals?
Absolutely. One of the issues that we have in moving heat around is that it's rarely where we want it, when we want it, and it's rarely at the temperature we want, when we want. So an awful lot of the excess heat, all this energy we're pumping into a hospital is at a very low grade, low temperature. We're dumping air out of the building at 75 degrees. You can't heat anything with 75 degrees. So a heat pump is a way to raise that temperature to a place where we can use it. But we also have the need for heat at times when we don't have enough heat in our buildings, and that's where storage comes in. The phase change storage allows us to store large amounts of heat in relatively small spaces, especially compared to using water, for example, where the specific heat is so low compared to a phase change material. But we can also, with their system, we can choose the temperature at which we store it. So if we want to take condenser water off a chilled water system at 85, 90 degrees and store heat at that temperature, we can do it. And then we can pull it out and use a heat pump to put it wherever we want it. Solar thermal is kind of a different take on things. My approach has been we have all this excess heat in our hospitals, let's use heat pumps. But maybe the better answer is let's use the sun and not run a heat pump to make the heat when we need it. But still, we know the sun only shines, about half the day. So there's a need for at least nighttime. And again, thermal storage, and maybe combined with heat pumps. So there's just, my head kind of spins with all the possibilities of things we could do here.
Great. Jim, thank you for opening us up to the possibilities. And indeed, that's the reason that we've come together. The purpose of the panel is really to activate your minds and get you thinking. What we want to do now is break out into our little workshop groups and explore together the possibilities so that together we can chart a new path forward for decarbonizing healthcare. In a moment, Jessica is going to open us up and send us to our breakout rooms. If you didn't pick one, she'll assign it. We're going to introduce ourselves. So introduce yourselves and say an idea, no matter how crazy, about how we might eliminate combustion in hospitals. Crazy ideas end up becoming good ideas in groups. So go ahead and say your crazy ideas. Then we're going to dig into some of these specific technologies and ask interesting questions. Why aren't they happening now? What are the barriers? How can we overcome them? What are side opportunities? What are adjacencies? How can we combine these together to help decarbonize healthcare? Dig deep into those topics. We'll have the opportunity to come back and share just our key takeaways. I'm excited about what's going to happen in these breakout rooms. Jess, go ahead and take us there. As folks are popping in, my hope is that you had some interesting ideation and then amazing depth of conversation on topics. And I'm sure there's a lot of thoughts that you've had that you'd like to explore further. We'll do a very little bit of that now, and then encourage you to share on the online community. Let's hear a key takeaway from each group. So starting with our heat recovery chillers 1. So Jim, do you or one person from your group want to take a minute or less to give a key takeaway from your group?
Jim, you're mute.
Go ahead, Kent.
Okay.
I'll use 10 seconds of yours.
Kent Peterson, and I'm going to do a minute. I'm hopefully going to give you more than one takeaway. So we talked about the true benefit of heat recovery chillers and heat pump chillers, and the ability between simultaneous heating and cooling that we see in healthcare facilities to allow us to basically get a very high COP and go all electric to replace some of the natural gas boilers that are out there. The other thing is if we can couple this with any type of thermal storage, it allows us to take the benefit of taking the diurnal temperature swings from day to night, be able to take heat that might be generated during the middle of the day, use that at night, and use the heat pumps as part of that system. We also talked about the very big difference between new construction projects in healthcare versus renovation or retrofit projects. And that these solutions are much easier to implement in new construction, where we can select the temperatures of the heating systems, whereas in retrofit situations and operating hospitals, it gets very difficult sometimes to implement these type of strategies.
Perfect. Kent, thank you for setting that awesome example. Next, Mark and Jess's group from Geothermal Heat Pumps.
Yeah, thanks, Troy. We had a great discussion about many topics, some on geothermal, but I guess more focusing on water. Just how water is an integral part of all of our decisions. Whether it's through how geothermal works or not. So we ended up focusing on waste to energy. How to use that as a method to capture some heat out of either sewage waste or something to that effect. Kind of like as Heather said, use the ground as a battery. And so we were talking about how that the challenge of messaging to a user group or a patient about how we're using the sewer water to provide heating in the building. There might be some issues on how that's perceived. So we want to make sure that that's would have to be discussed. But hospitals provide a lot of it's a pretty steady stream of fairly warm water in a lot of cases, and we're talking about if there's any condensate discharge that some hospitals have. So that's a pretty warm water stream that we should be able to reach out to and grab some heat and save some energy doing that approach. We did acknowledge that maintenance is a challenge, regulations are a challenge, but it could be a good way of managing our base load by capturing that extra heat.
So I will just add here, stay tuned. We're going to talk about that in an upcoming workshop.
Perfect. We're the straight man, right? For your perfect.
Perfect. Thank you, Mark. So next, Austin's group on solar thermal systems, I believe.
Yes. Yeah, we started by talking about a couple different ways, solar thermal and specifically solar PVT, PV plus thermal came up a lot. I think we all were in agreement that is a great opportunity and a great technology. And not to forget the addition of thermal storage. It's always an issue if you're generating during the day, but you need to use it at night. And so thermal storage, we briefly considered jumping into that room or stealing someone from that room. But we also talked about sizing solar thermal as the base load, using it to size the base load, and then using heat pumps or other methods to size the remaining loads. And another mention for shared renewables or community solar, if there's an opportunity to do that with a solar thermal or PV. We then did a scenario, either from the point of view of a hospital administrator or engineer, about what types of questions you would get if tasked with designing a solar thermal system for a hospital. And what are the loads, trying to predict the loads on an hourly basis. Maintenance came up as a potential barrier. Hospital staff are already pretty busy as it is, and adding more maintenance to their schedule is a considered barrier. And also trying to collect the data and design for the standard operating conditions. as well as the design conditions were key.
Awesome. Thanks, Austin. Cassidy, key takeaways from thermal storage.
Yeah, Chris Miller is going to give takeaways for our group.
Thank you, Cassidy. So one thing we talked about was how the materials now of thermal storage is plant-based, it's stable, it's biodegradable, it's better for the environment as opposed to previous thermal storage materials. The other takeaway is it allows decoupling of, using cooling and using heating to when you actually need it. And then finally, what we talked about is a new concept, which actually I tried using on a project, but it got VE'd out. But Steve Taylor has used and actually has written an article of using thermal storage between a chiller plant and a heat pump heating plant, and basically optimize the temperature for both. So you're essentially your COP in both making chill water and making heat when you need it on demand.
Awesome.
Chris, please go to Decarb Healthcare and get a conversation started on that specific idea.
Okay.
Perfect.
And we'll be talking.
Perfect. And then the group that I was in was also doing heat recovery chillers. I don't know if I gave him a good enough warning, but I'm going to ask Jeremy if he'll report the key takeaways.
Am I back?
You're back.
So we talked about heat recovery chillers, and we went over the basics of what heat recovery chiller is. It's a water-to-water hydronic system that moves heat from where it's being added to the building, moves it to where it's being used. We talked about heat recovery chillers in new buildings and in Washington State, and the new version of 90.1, the heat recovery chillers are now going to be required by code for healthcare. We talked about potentially using heat recovery chillers in existing buildings if you can get reset temperatures down low enough in moderate conditions. And I'm drawing a blank on what else we talked about. So,
Jeremy, I think that was perfect. I think you got the key takeaways. It's already happening in Washington by code, and there's opportunities elsewhere. It's happening in different places with different temperatures all around the country, and the opportunity is there. So we have.
And one last thing, that they're valuable in all climates across the country. So a heat recovery chiller makes sense in any hospital in the US.
Perfect. So we have 5 minutes left. Two things. Number one, we want to put all of these things to start to put them in conversations. I can see some of your eyes lighting up. And so I want to call, I didn't warn her ahead of time, on Dr. Monica Weiss to share or get us started on thinking about what the opportunities are as we start to use some of these technologies together. While she's doing that, Austin, if you can just be ready to quickly show Decarb Healthcare to everybody as a reminder. So we'll probably do both things simultaneously. Dr. Weiss, why don't you get us started?
So I could envision solar thermal, or working with a group of professionals and experts on how to use solar thermal on a campus level. So there are many opportunities for integrating solar thermal on the heating as well as on the cooling side. There are potentials for placing the collectors. So for example, on a roof or on a facade or for shading purposes, over a window or on a wall, and also when I put the picture in for the density, so you could see the shading underneath. So there could be a recreational area underneath, or parking spaces, whatever. So I think the solar thermal applications are not used in the most efficient, cost-efficient and energy-efficient way. There would also be an opportunity, for example, for district heating, so for the entire campus, and combining it with the campus loop for heating and cooling. And I think that's worth the investigation for it.
Perfect. Thank you, Dr. Weiss. Dr. Swapta, what did you learn from this session? Where are you seeing potential opportunities for decarbing healthcare?
I think a lot of interesting ideas and questions and concepts were presented. And from my perspective, as I mentioned earlier in the discussion, when we talk about decarbonization, I think maybe am I misunderstanding, or some of my colleagues here are misunderstanding. So the way I think about decarbonization is not 100% take the plug, unplug. It's actually taking it in steps. And when you reduce consumption and you shift and you use and you recover at all different aspects, yes, it might not be 100% in the Oxford Dictionary of definition of decarbonization, because I'm still shifting energy from one time to another. But when I have excess energy that's produced during a certain period of time, and I don't know what to do with it. And there are many examples in some states trying to pass that extra generation to neighboring state. Can I utilize this? And today, if we focus on applications such as solar, from solar thermal or solar PV, can I use the sun at midnight? Can I use the sun at 11 p.m.? And today, the utilization, you have to store that energy. Storing energy can be done either with batteries or chemical or thermal, many other technologies. So I believe today, if we were to focus on decarbonization on reduction, resilience, as well as utilizing all what's available for us from recovery of waste is one aspect. But as Chris said, also the ability to use thermal energy storage and add it into the whole plant as a whole. Am I better off adding a thermal energy storage on the inlet loop or on the outlet loop or between the cooling tower and the system? The ability that phase change technology today can be fully tuned at any temperature you want within a fraction of a degree and has a lifetime of 100 years or more. That gives you the full confidence you are adding something that outlasts the mechanical system lifetime, but also you are making the COP factors for all parts of the loop more efficient. And I want us to think about decarbonization is not just using something that does not use carbon at a specific time. It's actually using the energy that we use out from the carbon as like the solar or the wind. Can we use it when the wind is not there? Can we use it when the sun is not there? And I think energy storage plays a big role in this.
Perfect. Thank you, Dr. Swapta. Just as we are closing, Austin, you can go ahead and show decarb. And Jim, I'm going to give you the last word. Bring us home.
Okay. Is this a... While Austin's showing it, is that the point, Troy?
Yeah.
Okay. So the last word is we have lots of energy available to us. We need to find ways to use it more wisely through storage, through the sun, through heat pumps to move it around from where we don't need it to where we do need it. We just have to be more creative. But one of the key takeaways from the session I was in is that the vast majority of carbon emissions are going to come from existing buildings that have already been built. And we need to focus on solutions for those buildings as well as new construction.
Perfect. Thank you, everybody, so much. You can see the conversation doesn't have to end here. You have ideas that you're thinking of right now, go ahead and share them on Decarb Healthcare. Our next workshop will be Smart Water, Redesigning Domestic Hot Water Systems in 2 weeks. I hope that you and or your colleagues will be there, but as importantly, engage in conversations on decarb and elsewhere. Thank you all so much and have a great day.